We are Team Air. We're a sub-team of the Chicago Engineering Design Team. Here's our team. I'm Adam Beigel. I am co-captain along with Kaloyan Stalev here. Davin Doan is not pictured in this photo. Here's Ivan Martinez, Manh Phan, Kristen Sanchez, our pilot, Advik Sikligar, Frank Tarshis, Adrian Say, and Adrian Velasquez.
We start off talking about the technical design. The requirements and acceptance criteria for this include a mission time limit of 30 minutes, mission flight range of 12 miles, 10 minutes for the air drop, and a required flight speed of 20 to 25 miles per hour. For the air drop, we will have a descent altitude of 80 feet, 25 kilogram digital servo, a winch diameter of 100 millimeters or 4 inches, and a descent time of 1 minute and 44 seconds. For the camera, we need the target to be at least 40 pixels for accurate object detection, and we will be using an Arducam IMX477 with a 16mm lens to achieve the required resolution. The next topic is the imaging and ODLC subsystems. The first part of this is the hardware side, and as mentioned earlier, we're using an Arducam camera that records in 4K and also a 16mm telephoto lens in order to have the right optical zoom for finding the targets. To process the images and detect shapes, we have an NVIDIA Jetson Nano. Moving on to the software side of the subsystem, it includes a target location algorithm that returns a list of potential target coordinates. These then get cropped and passed to a color detection algorithm that determines the color of the targets. Finally, the most likely targets get passed into EasyOCR, which is a text detection deep learning library.
Before target location, we must have image preprocessing. The general process for this includes measuring the light intensity of the image and adjust the appropriate amount of brightness and contrast change. And finally, use the OpenCV erode function to reduce the white noise. So we are now left with an image that contains the targets in the image, and most of the runaway features are completely removed. The next part of the target location is color extraction. And basically, we extract the color of the targets before we search for target's contour. And since we do not know the color of the targets beforehand, we'll extract all the colors into masks, and later we'll find contour for each mask. So moving on to target contour. So once we got all the color masks, we will locate targets using OpenCV find contours functions. We also filter the targets based on its size and pixel density, and this way, too large or too small objects that happen to be the same color as the target we are searching for are disregarded. This is done by knowing the approximate size that the target should be given the current height of the drone. Then we crop the image and pass it on to the next step, color detection. First, we crop the target to the letter. Then we're gonna count the frequency of the colors that appears in the frame. So the color with the highest frequency will be the color of the shape, and the second highest frequency will be the color of the letter. So as you can see here, it's gonna detect orange with the highest frequency of 687. So orange will be the shape color. The second highest frequency will be green, and with a frequency of 201, so green will be the letter color. And the final phase will be text detection. And in here, we use the EasyOCR Python library. It's a pre-trained model that detects letters and numbers. But the problem is that EasyOCR cannot rotate text. So we're gonna attempt OCR on multiple rotations on the image of the targets. We also have to handle the case where EasyOCR makes some errors with the rotation of a letter. So it can read an M as a W or a Z as an N, or sometimes capitalize P as a lowercase d.
We're going to be going over our airdrop mechanism. The first thing we're going to be talking about, at least in this, for this airdrop mechanism, is the winch design. So the way this works is we have a servo motor attached to a spool used to wind wire, as you can see in the top right. The type of wire we decided to use was fishing line, as it is very durable, but it's also very small in diameter, meaning it doesn't take up as much space in the spool as well. The way we go about unwinding the wire is via an Arduino that is programmed to unwind the wire for a certain amount of time based on the altitude height of the drone. The way it handles this is via the Jetson. Now, given that our payload is a standard 16-ounce water bottle, which weighs about 0.5 kilograms, we decided to go about attaching the water bottle to the spool that is attached to the servo motor via a clip that is attached to the neck of the water bottle. And as you can see in the bottom right, all of this design was 3D printed and modeled in SolidWorks, and it was done with PLA to save time and weight with it.
Another design that we came up with was a brick design. In it, the water bottle would attach to a moon clamp, which would attach to a spool. The spool then spins a rotor, which can then be compressed using a paddle on the right and is activated through the movement of the servo on the left. This design is very similar to cars and bicycle brakes. And one feature we did add was a rotary encoder to measure how much the spool has rotated. And then from that, we can calculate how far the water ball has dropped. And using that information, we can find its velocity and acceleration. Another feature we had to add was we had to treat the mating surface of the paddle to increase the friction between the paddle and the brake rotor. This allowed for harder braking since there was more friction. Also, this design allows for variable speed control in two ways. First would be rapidly pulsing the brake on or off, similar to ABS in a car. Another way would be by changing how much the servo turns in the brake position, as the more it turns, the more pressure it's actually applying to the brake rotor. And the moon clamps are designed in such a way that if we brake hard enough, the water ball will just release once it's close to, and if we do this close to the ground, it'll fall within the region of interest while also being intact and not destroyed.
This next section is communications. We're using the MAV SDK Python library to communicate between the Pixhawk flight controller and the NVIDIA Jetson Nano companion computer through the telemetry port. Like the ground control station, this uses the MAVLink protocol to send information back and forth. We have a range of 2 kilometers for ground control station and 1 kilometer for a safety pilot, both of which exceed the 500-meter radius necessary for the mission.
This next section is going to cover the aircraft and autopilot. For our aircraft, as you can see on the right, it's a hexacopter design, and that's mainly due to the fact that if one motor breaks down or whatever, the pilot still has some control over the drone to be able to land it. And that's unfortunately happened to us before, where one propeller flew off and our pilot had to try to land the drone. And with our current drone design for this competition, we had to keep in mind the strength of the motors, which are 340 kV 6S motors, as you'll see on the next slide. And we never worked with these kinds of motors before because they were 5.3 kilograms of force at full throttle, so we had to account for that. And in order to do that, we decided to machine our own aluminum clamps for the strength compared to our previous design, which used PLA, which the aluminum is still pretty lightweight to adhere to our weight limit. The arms of the drone are carbon fiber because of the strength and rigidity, while also being lightweight. And we had to cut out our own 22-inch arms out of 2 6-foot-long tubes. The rest of the frame, the legs, base plates, and motor clamps are all 3D printed out of pretty much PLA and PETG. For the specifications of our drone, we initially wanted to go with two 6S 25 amp hour batteries in parallel design. On the right, you could see that we used the drone flight time calculator online to figure out pretty much our specs of the drone. With the 50 amp hour rating and the in 6S and the drone flight time being 30 minutes as per the competition, With those parameters being set, we figured out that our all-up weight of the drone had to be around 10.5 kilograms.
Here's our autopilot setup. We are using the PX4 firmware on a Pixhawk 6C flight controller, which has an SIK radio connected to it. In the image here, we have our ground control station with the other SIK radio attached via USB. Our goal is to have waypoint updating based on the ODLC system from the Jetson Nano to take control of the drone and then move to where we needed to be for the mission. Next section will cover obstacle avoidance. Our plan here was to use this TF Luna LiDAR sensor, which has an operating range of 0.2 to 8 meters. It connects directly to the Pixhawk and the measurements can be interpreted by the PX4 autopilot. Here on the bottom we can see the current distance reading, which is coming from the sensor. PX4 can then interpret this and make adjustments to the flight path as needed. We did not get the chance to test this in a flight mission though.
Now moving on to the alternatives and safety aspects of our drone. In this section, we'll be talking about the alternatives we considered and the safety measure we took when designing our drone. We considered many alternatives during the design process. For example, in our Autopilot program, we decided to stick to PX4 firmware over Autopilot since the flight controller we had was Pixhawk, which was designed for PX4 in mind. And from our research, it seemed more of a straightforward implementation when compared to Autopilot. In terms of the airdrop mechanism, one of the airdrop mechanisms we considered was a small box with a door on it that would open and release the water bottle once it had reached the ground. However, this added quite a bit more load to the drone and required a second battery and controller attached to the case. On top of that, we also had the ultrasonic sensor on the bottom to detect it as when it reaches the ground to release it as well, but the ultrasonic sensors are not very accurate in their measurement, as well as if the case did not land flat on the ground, the ultrasonic sensor would not read proper values in order for the water bottle to drop. In terms of the obstacle avoidance, we considered surrounding the drone with several ultrasonic sensors, but as mentioned previously, those are not very accurate in their measurements, and we were not able to read accurate data fast enough in order to avoid collision with other drones. Lastly, when comparing 6S and 12S battery systems, we switched over to 12S as it allowed us for higher voltage for the drone, meaning the drone will be performing more efficiently since it'll be more power delivered to the motors. Moving on to safety risk and mitigations. One of our main concerns for safety was avoiding any possible issue with the drone. We tested autonomous flight in a low clear area at low elevations, monitoring from a safe distance. If we did crash, we inspected the impact areas after every flight to make sure nothing was broken. We also used plastic propellers on the test dummy drone to minimize the damage done to anything that the propellers hit, because the carbon fiber propellers can do a lot more damage. In terms of the drone components falling in flights, one way we went about reducing this, the components falling, we used nylon lock nuts and lock teeth to secure the hardware. As we talked about before, we chose the hexacopter design over the quadcopter design so that we have some redundancy in case a motor or propeller falls. And as previously mentioned, we have planned to change over from 6S to 12S in order to prevent overheating to our electrical systems. Lastly, we had several of our team members take the recreational UAS safety test, and we have also registered our drone with the FFA.
Now we talk about the flight readiness portion. For the imaging and ODLC performance, we created a script to automate digital target creation to be able to create thousands of images against our ODLC subsystem and ensure accuracy with simulations. Next, the randomly generated targets were placed on a Google Maps image of the competition runway, and the team was able to fine-tune the algorithm to detect targets. Finally, we tested against real images taken using a GoPro. We also performed tests on the text detection algorithm to see how accurate it was. We generated many combinations of targets with different rotations, shapes, colors, and letters. As you can see, there are some letters that are more accurately detected than others. Overall, the average accuracy for the text detection was 78%. A lot of the work was done in simulations. Since we are in the middle of a city and are pretty close to an airport, we cannot safely fly our large drone autonomously. Because of this, we do short test flights at low altitudes. Then for longer autonomous flight tests, we took the drone to an airfield in a nearby suburb. For these lower flights, we used a GoPro camera to take photos of the targets at the correct resolutions.
Now moving on to the airdrop performance of the first airdrop mechanism of the winch in this case. One of the unique challenges we faced when designing the spool, how big the spool should be, was the fact that given the servo motor its speed was limited based on the voltage we could output. In this case, the Arduino would output 5 volts to the servo motor. The speed at which the servo motor would rotate was about 44 rotations per minute, which is not very fast. So only thing we could really think of was to increase the diameter of the spool, which allows more wire to unwind within every rotation. Now, there is a trade-off to this. Obviously, as we increase the diameter of it, we increase the size that the spool itself takes up, which in and of itself increases the weight of the spool as we are 3D printing this. But given the fact we at 100 millimeters, we decided that was the most optimal size for the diameter of the spool, as we were able to get the descent time under 2 minutes.
When it comes to aircraft performance, we were able to test multiple flights with our dummy drone, but unfortunately, due to time and part availability, we weren't able to test our actual drone. Regardless, we still designed it to be quite strong with the materials we had available, and we ran a ton of simulations within SolidWorks to mainly test the displacement of the carbon fiber arms. And if you look to the right, that is the simulation. If we basically strapped the drone's legs to a table and went full throttle with the motor, and the rated force for those motors is 5.3 kilograms of force at full throttle, and the displacement of that would be around 9 millimeters.
We conducted 2 tests using our test dummy drone, pictured here on the right. In the first test, we manually flew up to 25 feet, then had the drone hover for a few seconds and autonomously land. We'll see a demonstration of this next. The other mission we attempted was to autonomously take off, ascend to 25 feet, hover, fly some waypoints, and then land autonomously, but unfortunately the drone crashed after reaching the target altitude. Because of this, we did not conduct any tests with the much larger competition drone for safety reasons. This is our flight video of our successful hover and autonomous landing from April 1st at Miller Meadow. So he's hands off right now. Yeah. Yeah, it's fighting the wind a lot. Perfect landing.
We move on to the proof of safe flight section. For this section, we only met a certain amount of criteria. Some of these include flying waypoints with a max error of 25 feet, a turn radius of 150 feet and be able to stay within the mission flight boundary, and angle of climb and angle of descent of 20 degrees.
This is the flight video of our competition drone where we tested its manual takeoff and landing capabilities on April 26th.
I'm gonna land it, okay? Yeah. But getting it up, that's a bit of an issue, so we don't put it in the landing. Hey Chris, that's up. It actually is flying kind of well. Well, the point is good. Once it's up, yeah, once it's up in the air, it's good. There we go.
So this was our first year attending this competition, so we were starting almost entirely from scratch. We had a lot of challenges when figuring out our design process and trying to get our parts ordered on time. Next year, we're going to be attempting more flight tests early in the school year now that we have parts to work with. Something that did go well was our attempt at rapid prototyping. We made extensive use of our shop's 3D printer when creating new parts and iterating on old ones, which allowed us to test different designs much quicker. We also learned that we need a bit more structure when developing for the software side. More thorough planning would make the process much easier and prevent us from having to redo some of our work. We have high hopes that next year we will be able to attempt the mission at the competition. Thank you for watching.